Okay, we begin with the 2015 one, question 13. Now remember, how many questions are there now? It's 10 multiple choice, then another 6, so it's about midway in 13. You usually find, I mean it changes, not always every year, but you usually find that you're going to get one question where it's just playing with the properties, simple stuff. You know, find tangents, normals, that sort of thing. And another one which might be a locus. So you might get a couple of conics questions. So here we've got two hyperbolas there. They've got the same asymptotes. Yep. And so they've given us the parametrics for P and Q. So basically they've set the question up for us. So the first part is simply verify that Q, those parametrics do satisfy the hyperbola. So a little bit of a gift question to start off with, so we can get some marks. So all we really need to do is substitute into the equation of the second hyperbola, and we end up with tan squared minus x squared, which is -1. And that was the equation, I believe, hang on, let me go back to the diagram. Yeah, so notice they didn't change the sign on the x squared and the y squared. Instead, they changed the sign on the -1. So it is actually one where the y squared is positive, which is why the foci are on the y-axis. Next, and they've said show that, so we can't quote it, PQ, so let's actually derive the equation PQ then. Find the slope, and it comes out quite nicely there because we've got tan theta minus sec theta, which will cancel, minus b on a is our slope. Point slope formula. And well, they've told us how they want the final answer, so I just have to rearrange that and we get the expression they want. Again, not too bad. I mean, here comes the interesting bit, the property. Prove that the area of triangle OPQ is independent of theta. So in other words, we should be able to eliminate the parameter. There'll be no parameter in there at all. So I'm going to find the perpendicular distance from O to PQ. And I've done that using the perpendicular distance formula. You notice I was able to get rid of the absolute value sign because I know A and B are positive numbers. We assume they're positive. And theta is an acute angle because of the position that they've put P in. I know that theta is going to be acute. So I know AB tan theta plus sec theta must be a positive number there. And then I'll just use the distance formula to find PQ. We've got a bit of trig identity work to do in there, have we? So some sec squareds. Oh no, it's just a common factor, my mistake. Common factor, because of course sec minus tan squared is the same as tan minus sec squared. We're squaring a negative number. So there is actually a common factor there. I made it tan minus sec rather than sec minus tan. I guess so it just matches up with the order in the perpendicular distance formula there. And so square root of that, okay. So area is half of base times height. I want to get rid of the thetas. Gee, would have been nice if that was, oh no, that's all right. Because when I multiply that out, I get tan squared minus x squared, and tan squared minus x squared is of course 1. Let's go back to 2014, also in the middle of the paper. Boy, look at those coordinates of M. But they've given it to us. Remember, if they give you stuff, don't waste time deriving it. They're trying to save you some time here. Okay. Show that M also lies on the hyperbola. Yes, and you can't say, oh, look at the diagram. It's on the hyperbola. That's not showing it. You've actually got it. All right. So there's our coordinates M. Again, I guess the easiest way is substituting in. And let's see what happens. Eventually, a lot of algebraic fraction work there to do, but eventually we do come down to be 1, and that's what we're expecting. So you can see, look, there's always some nice simple marks to grab out of it. So here's the property we're trying to prove. Prove that the line through P and Q is a tangent to the hyperbola. Okay, well, what did I do? I said, well, slope PQ, let's find the line that goes through P and Q. The slope of PQ And then I'll also find the slope of the tangent. Hopefully I can show they're the same thing. So divide the x as b squared x on a squared y, sub in m, and I do get that it is a slope. So either they're the same line or they're parallel. So I know at this stage, best I can say, PQ is parallel to the tangent there. But we already know that M lies on the line PQ. So therefore, it's not parallel to it, it must be the line PQ. Oh, it goes a bit further. Eh? Show that OP times OQ is OS squared. Oh, well, OP times OQ, distances when we're joining them up to the origin are usually quite easy to find. So we get square root of a squared t squared plus b squared t squared times the square root of a squared on t squared. So I factorised out the t squared from the surd to get t out the front. The second surd I factorised out the 1 on t squared to get 1 on t. So the t times the 1 on t cancels. I've ended up with the square root of a squared plus b squared times the square root of a squared plus b squared, which is a squared plus b squared. We're talking about a hyperbola, so a squared plus b squared is a squared e squared. Remember, e squared is equal to a squared plus b squared over a squared. We'll multiply through by the a squared, we get the a squared plus b squared. That, of course, is the length of OS. We know the coordinates of the focus is AE. So we've got OS squared. Now, if P and S have the same x coordinate, show that MS is parallel to one of the asymptotes. Well, therefore, if P and S have the same x coordinate, and we know the x coordinate is AE of the focus, so therefore AT, which was the x coordinate of the point P, AT must equal AE, so our parameter we're playing with is actually E, not T. So if we find the slope of MS, because we're trying to show it's parallel, but now using AE, then it does come out nicely, doesn't it? The slope of MS, again, a lot of algebraic fraction work. We get minus B on A, which we know is the slope of one of the asymptotes. There was another one in 2014. This is one dealing with the ellipse. So parametric, we've got our tangent and our normal marked in. Show that the tan of phi is a squared minus b squared on AB sine theta cos theta. Right, well, we've got to find that angle in there. Well, x is a cos theta, so I know dx to theta is minus a sine theta. Basically, I'm finding the slope of the tangent, but I'm using the parametrics. So dy to theta is b cos theta. I get dy dx is minus b cos theta on a sine theta. So there's our slope of our tangent. That allows me to find the slope of the normal. It'll be a sine theta on b cos theta. So okay, I know that angle. I'm now going to find the slope of OP, and the question really then becomes the angle between two lines. So OP, well, we're just joining up to the origin, so it'll be b sine theta on a cos theta. So tan minus tan on 1 plus tan tan. Although slopes we're using for this instead of tan. Yeah, it looks ugly, but you know, you look at the denominator at the top, look at the denominator on the bottom. It's going to cancel nicely. I've just multiplied by cos squared. So the bottom just becomes cos squared plus sine squared. Well, that's nice. The top, though, we're left with a b on the bottom of the first fraction, and a on the bottom of the second fraction. So let's play around with that. That now has a common denominator of ab. I get a squared sine theta cos theta minus b squared sine theta cos theta. We get a squared minus b squared on ab, absolute value of sine theta cos theta. Now, this is where on that particular year I said, well, okay, if P is as illustrated in the diagram, then we know theta is acute. So I can say that sine theta and cos theta would be positive. So I get the result that they're looking for. So I just felt I needed to explain why I could get rid of those absolute value signs on that one. Find the value of theta, which phi will be a maximum. Okay. Well, we know that sine theta cos theta is a half of sine 2 theta. We know that's a maximum at the amplitude, and sine curves are always a maximum at pi on 2. So 2 theta would be pi on 2. I know theta is equal to pi on 4. Now our expression, remember, was a squared minus b squared on ab times sine theta cos theta. Well, we know a squared minus b squared on ab, that bit's going to be constant. That's not going to change. So tan phi is a maximum when theta is pi on 4. And as tan phi is an increasing function, then I know that has to be a maximum. So phi is a maximum when theta is pi on 4. So it gets a lot of just playing with trig identities and trig properties to get some of these out. I mean, yeah, sure, I suppose a lot of people probably wasted a lot of time by going, oh, I got to find, oops, I've gone too far. I've got to find when it's a maximum. Oh, let's use calculus. But again, as I said before, use your knowledge of trig functions can save you time. Because I guess, in case you're wondering, hang on, whoa, I still haven't quite got that. Remember, that's the expression that we had. They were asking us to say when phi was a maximum. But if you think of your tan curve, tan phi is a maximum when phi is a maximum, because it's continually increasing. So that was the bit I had in my answer about it. Hey, it's always increasing. Okay, let's move on to the next one. So 2013, oh, I did like this question. I do remember it now. 12D, it was a nice one, in my opinion, for what it's worth. It is a rectangular hyperbola this time. And we've drawn in two tangents. Absolute value of P does not equal the absolute value of Q. Now the reason that's important, if they did, then those tangents would be parallel. We don't want that. Okay, so they've set up the question for us. Starts off again with some nice quick marks. Just show the equation of a tangent. So all right, y equals c squared on x. Let's differentiate it. Sub in, we get the slopes minus 1 on p squared. Point slope formula. Bingo, we've got a nice, I should imagine that was only worth 1, but at least we picked up that mark. Show that A, B and O are on a circle with centre P. All right. Well, I know that triangle AOB is a right angled triangle. So remember, A and B are on the axis. And AB must be the hypotenuse. So we know AO and B is concyclic. Because whenever you've got a right angled triangle, you've got angle in a semicircle. And so AB must be the diameter. The hypotenuse turns out to be the diameter with a right angled triangle. The centre, therefore, is the midpoint of AB. Okay, so we just need to show that the centre of the midpoint of AB is the point P. So let's find the coordinates of A. We can substitute into our equation of a tangent. We get the x value is 2cp at A. For point B, the y value is 2c on P. So the midpoint of AB turns out to be CP, C on P, and they were the coordinates of P. So yes, the centre of this circle is the point P. Now, I've redrawn the diagram for this because I think we're going to need it. We have to prove that BC is parallel to PQ. There's lots of different ways of doing this, but this is how I did it. I drew in 3 lines. I joined up BC, I joined up PQ. That made sense because we're trying to prove they're parallel. But the other one I joined up was AD. AD. Okay. We know P is the centre of a circle that passes through A, B and O. We proved that in part 2. Now, similarly, Q, therefore, must be the centre of a circle that passes through D, C and O. Again, the advantage of using parametrics. We generalise the situation, we can apply it. So, all right. So therefore, AP is equal to BP, but we also know DQ is equal to CQ. So the ratio AB to BP is the same as DQ to CQ, is 1. And we've got ratio of intercepts, therefore, of parallel lines. So therefore BC is parallel to PQ, is parallel to AD. I think that's possibly the quickest way of doing it.